Hey everyone and welcome back to the channel. Ever wonder how all those virtual machines in the cloud scattered across dozens of different physical servers actually talk to each other? How do you keep them secure and organized without manually configuring hundreds of switches and firewalls? If you ever felt like cloud networking is a black box, you are in the right place. Today we are demystifying one of the most powerful components of OpenStack, Neutron, the networking service. In this video we are going to break it down for beginners. We'll start with the basics, explore Neutron's architecture and then get hands-on. You'll learn how to create virtual networks, subnets and routers and see exactly how OpenStack connects your VMs not just to each other but to the entire internet. So grab your coffee and let's get started. First, let's understand the core problem that OpenStack Neutron is designed to solve. In a typical private cloud, you have several compute nodes and each one is running multiple virtual machines for different applications and users. So we have two main goals. We need to establish communication between these VMs, even when they are running on separate physical machines. At the same time, we must isolate certain VMs from others for security and organization. For example, you probably don't want your public-facing front-end web server to be able to talk directly to your sensitive database servers. So, how could we solve this with traditional networking? We could set up a few VLANs that span across all our compute nodes. It would be a classic multi-tier approach. One VLAN for the front-end, another for the back-end, and a third VLAN for the database. Then we'd need to configure inter-VLAN routing on our physical router, set up DHCP services, and add a bunch of firewall rules to control the traffic between those zones. Technically, that would work. However, this approach has some serious downsides. It's slow and complex as manually updating configuration on physical switches, routers and firewalls for every change is incredibly time-consuming. Also, it creates bottlenecks. Most developers don't have access to the core networking gear. They have to submit a ticket to the network team and wait every time they need a new network or firewall rule changed. This is exactly where Neutron, the OpenStack networking service, comes in. It's running alongside other core OpenStack services. Neutron is the component responsible for creating and managing this entire networking framework as a virtualized service. What's brilliant is that OpenStack networking model closely mirrors traditional physical networking. It uses familiar concepts like routers, switches, and subnets. The key difference? It's all virtual. It's all software. When you run out of Ethernet ports, you don't need to buy new hardware. You just create more resources with just a few clicks or a single API call. Your developers can get a self-service portal to easily create new networks that span across multiple nodes, attach VMs and configure IP addresses, implement firewall rules through security groups. Moreover, Neutron handles all the backend complexity like routing between networks and ensuring automatic IP allocation. Because it's all software-defined, this entire configuration can be stored as a code in a repository, infrastructure as a code. This not only gives you version control and change tracking, but also allows you to perfectly recreate the same complex environment in a different region with ease. And the best part? You don't have to change anything on your physical routers or switches, as long as there is a basic layer 3 IP connectivity between your compute nodes. Neutron overlays the rest. This virtualized model is what enables true multi-tenancy. Each project or tenant can have its own completely isolated private network with its own routers and IP address spaces, all running securely on the same shared physical infrastructure. There's no risk of traffic leaking from one tenant to another. So now that we understand why Neutron is so powerful, let's dive into how it actually works. Let's break down OpenStack Neutron's architecture starting from the top. The main component is the Neutron server. You can think of it as the brains of the operation. It runs the Neutron API service, receives all the network requests, and acts as a central controller. In Kola Ansible deployments, the Neutron server runs inside a Docker container. We can quickly verify that with a simple command. Neutron Architecture is built to be flexible using a powerful plugin system. This allows you to swap out different backend technologies from various vendors without having to change Neutron's core code. One of the most essential and widely used plugins is the modular Layer 2 ML2 plugin. It's the standard for handling Layer 2 networking. Let's peek into our ML2 configuration file, which is also inside the Neutron server container. Inside this file, you'll find a few key settings like type drivers. These define the kinds of network technologies available. In our setup, we can see support for flat networks, a simple unsegmented Layer 2 domain, VLANs, for 802.1q tagged networks, and vxlan, which creates overlay network encapsulated in UDP. Then, Tenant network types. This sets the default network type for users. Here, it's set to vxlan. So, every time a user creates a new private network, Neutron automatically provisions it as a vxlan. Then we have mechanism drivers. These drivers define how the virtual networks are actually built and managed on the hosts. Popular choices include openvswitch (OVS), Linux Bridge, and OVN (Open Virtual Network). Our deployment uses the very common OVS driver. Then there are network-specific configs. You'll see the configuration like the range of VNI IDs that can be assigned to new networks and so on. So when the Neutron server gets an API request, like create a new virtual port, it doesn't do the low-level work itself. Instead, it uses the ML2 plugin to pass the task to the correct agent on the ground. These agents are the distributed workers that configure the networking on each host. Just like the Neutron server, these agents also run as Docker containers. We can list them with OpenStack and Docker commands. You'll see several types of agents, each with a specific job. OpenVSwitch agent manages the local virtual switch on each node. DHCP agent assigns IP addresses to VMs. L3 agent handles routing between networks and provides NAT services. Now a critical point. Where do these agents run? Centralized services like the DHCP agent and the L3 agent typically run only on the dedicated network nodes. Think of it like a physical network. You might have 50 servers, but you only need 1 or 2 central DHCP servers for the entire rack, not one on every machine. But wait, you may ask, if the DHCP and L3 agents are on different nodes, how do my VMs running on compute node get an IP address or reach the internet? That's where OpenVSwitch agent comes in. When using OVS, the OVS agent runs on every single node that participates in the virtual network, including all the compute nodes. This agent is responsible for creating and managing the local virtual switch and connecting it to other nodes, creating a seamless Layer 2 fabric. We can confirm the OVS components are running on compute node. Because this OVS agent provides a Layer 2 connectivity across all nodes, a VM on any compute node can easily send a broadcast to find the DHCP agent on a network node and get its IP. It's this distributed agent model that makes Neutron networking magic happen. Before we move on, there's a crucial feature of the OpenVSwitch agent we need to cover. Its firewall capability. The OVS agent doesn't just provide Layer 2 connectivity, it's also responsible for enforcing security group rules. The specific mechanism used for this is determined by the firewall driver setting in the OpenVSwitch agent ini file. You'll typically see one of two main options. IP tables, that's the hybrid mode. This is a common default. It's called the hybrid mode because in addition to OVS, it uses traditional Linux networking components like Linux bridges, VETH pairs, and IP tables to filter traffic. While it works, this approach adds complexity and performance overhead. Another option is OpenVSwitch, the native mode. This is a much cleaner and more efficient approach. The native OVS Firewall implements security group rules directly as open flow rules inside the OVS data path. This eliminates the need for Linux bridges and IP tables for filtering, resulting in lower latency and higher throughput. For better performance, let's reconfigure our environment to use the native OVS Firewall. We'll do this by providing a custom configuration file that Kola Ansible will use to override the default settings. First, let's create a dedicated folder to store our custom Neutron configuration. Now, let's create a new configuration file and set the firewall driver to openvswitch. Finally, let's run the Cola Ansible deployment playbook. This will apply the new configuration and restart the Neutron openvswitch agent containers across our cloud. Once the deployment is complete, we can verify that the change was successful by inspecting the agent's configuration file again. The firewall driver is set to openvswitch. With this simple change, our cloud is now using a more efficient and performant firewall mechanism. In OpenStack, you'll hear about two main types of networks: tenant networks and provider networks. Let's break down what they are and when you'd use them. Think of a tenant network as your own private project-scoped network space. These networks are created and managed by you, the user, also called the tenant, inside your OpenStack project. The key thing to understand is that those are overlay networks. This means they run virtually on top of the existing physical networks. OpenStack achieves this through encapsulation. It takes the traffic from your virtual machine, wraps it inside another protocol like vxlan, gNIF or GRE, and sends it across the physical infrastructure. When it reaches another OpenStack compute node, it's unwrapped and delivered to the destination VM. Your network traffic is completely separate from other tenants, even though you're all using the same physical hardware. Moreover, you can create thousands of these virtual networks without ever having to ask network administrator to configure a physical switch or router. In our setup, we are using vxlan encapsulation as it's the most common type. It supports up to 16 million unique networks. Now, a provider network, on the other hand, is a direct bridge to a physical network that already exists outside of your OpenStack cloud. These are created by the administrator, not the tenant. Think of this as plugging your VM directly into a real-world network, like your company's corporate network or a direct connection to the internet. Provider networks don't use overlays. Instead, they map directly to physical network technologies. Provider network can be flat. This puts your network onto a single physical layer 2 network. It can be a VLAN. This maps your virtual network directly to a specific VLAN on the physical switches. This is a very common way to connect OpenStack to existing enterprise networks. Or it can be routed, which allows your VMs to receive IP addresses from externally routable subnets, enabling direct access without NAT. Just to sum up, a tenant network is a private network that interconnects your VMs and is used for east-west traffic. And a provider network is an external network that connects your VMs to the outside world, handling north-south traffic. Let's see how this all works in practice. For two VMs on different nodes to communicate, they first need a common network. Think of OpenStack network as a distributed layer 2 virtual switch that can span multiple physical servers. It's a logical container for your subnets. Let's create one now, and I'll call it my network. When you inspect the network's properties, you'll see important details like MTU and the underlying network type, which is vxlan in our case. Next, we need to define a subnet. This is a layer 3 concept that specifies the IP address range for your VMs. To create a subnet, we need to provide the network it belongs to, an IP address pool, a gateway, and a DNS server. If we look at the subnet details, we'll see that DHCP is enabled by default. This means any VM we attach will automatically get an IP address, gateway, and a DNS information. In OpenStack, VMs don't connect directly to a network. They connect through a port, which is like a virtual network plug. A port holds the MAC address, IP address, and security group information for a connection. Let's list the ports in our project. That's interesting. There's already a port here, but we haven't created any VMs yet. So, who is using it? Let's inspect the port's device owner. The owner is the DHCP server for our subnet. This makes perfect sense. The DHCP agent needs a port to provide IP address to VMs on this network. It's typically assigned the .2 address in the subnet. We can see which nodes are running our DHCP agent with this command. As I said earlier, our DHCP agents run on the network nodes. In this two-node lab, both nodes have both compute and network roles. So, how does the DHCP agent connect to this network? It uses a powerful Linux feature called network namespaces. A network namespace is an isolated copy of the networking stack with its own interfaces, routing tables, and firewall rules. Let's list the networking namespace on this node. You can see a namespace starting with qdhcp. This is where our DHCP service lives. Let's jump inside it by running a bash shell within that namespace. Now that we are inside, let's check the interfaces. There it is, a tab interface with the .2 IP address assigned. The DNS mask process, which acts as our DHCP server, is using this interface to listen for requests. Okay, let's exit that namespace and get back to creating our VM. We now have a network, a subnet, and a DHCP service ready to go. Let's create a dedicated port for our first VM. This gives us more control, allowing us to assign a specific IP address. I've specified a subnet, a static IP, and a name. If you omit the IP, one would be assigned automatically. Notice the port has a MAC address, but its status is down because it's not attached to anything yet. Now let's create the VM. Instead of specifying the network, we can directly provide the port we just created. After a few moments, if we list the ports again, we'll see the final result. The port status is now active and its owner is Compute Nova. And just like that, our VM is live and connected to the network through the expected port and IP address we defined. In a traditional networking, physical switches connect devices on a layer 2 network, forwarding Ethernet frames based on MAC addresses. OpenVswitch brings this concept into virtual world. An OVS bridge is essentially a software-based virtual switch. It connects various network interfaces, like those for VMs, physical NICs, or even network tunnels, allowing them to communicate as if they were all plugged into the same physical switch. In a standard OpenStack deployment, OVS uses 3 distinct bridges on each network node to separate and manage different types of traffic. Let's take a look. From this output, we can identify 3 critical bridges. The integration bridge, this is the central hub. All virtual network interfaces for VMs connect here, as do the special tab interfaces for services like DHCP server and virtual routers. If we look at the port on integration bridge, we'll see the interfaces for the VMs and DHCP server we created earlier. Notice they share the same tag, which places them in the same virtual network. Then there's the tunnel bridge. This bridge handles all the overlay network traffic between our nodes. When a VM on one compute node needs to talk to a VM on another compute node, the tunnel bridge encapsulates the traffic into a vxlan tunnel and sends it across the physical network. It's the key to making our private Tenant network span the entire cloud. Lastly, there's the external bridge. This is our gateway to the outside world. The external bridge connects to a physical network interface like ETH1 in this example and manages traffic to provider networks and floating IPs. It's what allows our VMs to reach the internet and be reachable from the outside. So, how do these 3 separate bridges work together? They are connected using patch ports. Think of a patch port as a virtual network cable that directly links 2 OVS bridges. If we look at the configuration again, we'll see a patch port on brint connects to corresponding port on brtun, and another patch port on brint connects to a corresponding port on brx. This stitching creates a complete path for network traffic. A packet can travel from a VM on integration bridge, cross over to external bridge to go out to the internet, or cross over to the tunnel bridge to be sent to another node. This interconnected design is what makes OpenStack networking so powerful and flexible. Let's dive back into ports. Think of it as a VM's virtual network interface. It holds IP address, MAC address, and security group settings, defining exactly how the VM connects to the network. Creating a port prior to creating a compute instance is very handy. You can detach a port from one VM, attach it to another, and keep the same IP and settings. This is especially useful during failover scenarios where you can move the IP from a broken instance to a new one, or during upgrades or migrations where you can swap infrastructure without changing the DNS. Think of it like unplugging a cable from one server and plugging it into another, except you are also moving the entire network interface, not just the connection. When creating a VM, a port can be created for you automatically. The only thing you need to do is provide the network. Let's create another VM. This time I will provide only the network. In this scenario, Nova will ask Neutron to create a port and then connect the VM's virtual NIC to that Neutron port. Mind that if I delete VM2, then the port will be deleted along with it. However, if I delete VM1, that's the VM we did assign the port manually, the port remains. It's just down, not assigned to anything. Let me remove it. Let's now shift gears and look at communication between VMs. We'll start by looking at how two VMs can communicate even when they are running on different physical compute nodes, as long as they belong to the same subnet. Let's begin by creating our first VM. I will call it VM1 and place it on stack 1, which is our first compute node. Now let's create VM2 on stack 2, our second compute node. To confirm their placement, let's quickly check where VM1 is running. Excellent, it's on stack 1. And VM2? Perfect, VM2 is on stack 2. So despite those two VMs being on separate physical hosts, they are both connected to my network and thus belong to the same IP subnet. Let's verify their IPs. Now let's test the connectivity. We'll access VM1's console. First we need to find its name on the operating system. Okay, once we have the instance name, let's attach to it console. Now from within VM1, let's try ping VM2. I will use the VM's 2 IP address, which we saw earlier. And there you have it. It works. Even though VM2 is on a different physical node, we have direct reachability because both VMs are part of the same subnet. Now, let's take a look under the hood at the OVS configuration on stack 1. What's really interesting here is the new vxlan port. This port, visible on the tunnel bridge, is the key to how this cross-node communication works. It creates an overlay network between stack 1 and stack 2, essentially tunneling the VM's traffic between them. So, to summarize what we've seen, the virtual network we created seamlessly spans across multiple compute nodes. As long as VMs belong to the same subnet, they can communicate with each other even if they reside on different physical compute nodes. This is all made possible by openvswitch leveraging technologies like vxlan to create overlay networks. Essentially, vxlan encapsulates layer 2 Ethernet frames into UDP packets, allowing them to traverse an IP network and span across different physical hosts. What if we create another subnet within the same network? Let's create one and name it MySubnet2. Now we effectively have two subnets operating within the same network. To confirm this, we can list our subnets. Next, let's create a new port specifically for MySubnet2. We'll name it VM3 port. With our new port ready, let's provision a new virtual machine, VM3, and attach VM3 port as its network interface. If we examine our list of VMs, we'll see that VM1 and VM2 resides in the 10.128 subnet, while our newly created VM3 is assigned to the 10.129 subnet. Now let's connect back to the console of VM1 to test connectivity. From VM1, let's attempt to ping VM3, which is in a different subnet. Connection fails. Let's investigate the routing from VM1 to understand why. As you can see, the route points to the default gateway, which is 10.128.0.1. Let's try ping that default gateway from VM1 as well. Doesn't work. This is precisely what we expect. Even though these subnets belong to the same network, they are by default isolated from each other. This demonstrates the segmentation capabilities of OpenStack subnets. How to address the lack of communication between two subnets? In the real world, you typically use a physical router to connect different network segments. In OpenStack, you have the same concept. An OpenStack router, that's a virtual layer 3 device that connects different Neutron networks and enables communication between their subnets. Let's begin by creating our OpenStack router. We'll name it MyRouter. Now the crucial step. We need to connect our subnets to this router. First, let's connect MySubnet. Then, we'll connect our second subnet, MySubnet2, to the same router. With both subnets now linked to the router, we can finally test for successful connectivity. Let's head back to the console of VM1. From VM1, let's try ping VM3 again, which resides in my subnet 2. Success! The ping now works. The reason for this is that VM's1 default gateway now points to the router, which is intelligently routing traffic between two connected subnets. To confirm this, let's inspect the routing table on VM1. We can see that the route indeed points to the default gateway, our newly created router. Let's even try ping this gateway. Works. From the underlying operating system perspective, an OpenStack router is implemented as a network namespace. Let's list namespaces on our OpenStack control plane to see this in action. We have a namespace prefixed with qrouter. This is our router's dedicated network namespace. Let's dive into it to inspect its configuration. Now, within the router's namespace, let's examine its network interfaces. There are two QR interfaces. Each of these acts as the default gateway for one of our connected subnets. Let's also look at the routing table within the router's namespace. This clearly confirms that our virtual router is fundamentally a Linux network namespace equipped with multiple interfaces, acting as the central point for inter-subnet communication. To understand how this integrates with openvswitch, let's inspect the OVS integration bridge. We see that the QR interfaces are plugged into the OVS integration bridge. It's important to note that the IP address assigned to each router interface on a subnet is the same as the gateway IP that we've defined when we initially created that subnet. What if we have a VM on a totally different network? Let's try that and see what happens. I will create a new network. Let's name it My Network 2. Then within that network, let's create a subnet. Finally, let's create a VM within that new network. Can this new VM talk to a different VM in a totally different network? Sure it can. We just need to connect this subnet to our router. Let me do that now. If we look at the networking topology, we see that the router now interconnects three subnets. So, a router can not only connect subnets within the same network, but also subnets between different networks. Finally, what you would like for our VMs to be able to access the rest of our network or the internet? As you suspect, we just need to attach the external network to our router. To do that, let's first create a provider network and name it public. As we'll be connecting to the outside world, we need to mark the network as external. Here we specify the physical network mapping. Flat means there will be no VLAN tagging. All traffic is untagged. You'll ask, why FizzNet1? In ML2, we declare FizzNet as a valid flat network. Then the provider network named FizzNet1 is associated with the bridge BRX in the OVS agent. Finally, the ETH1 physical interface is connected to the external bridge. As we have our provider network created, let's create a subnet and attach it to our network. I'll set the default gateway for the subnet to the IP of our external router. Then I will set IPs from 12.100 to 12.120 for assignments to VMs. That's an unused slice from my public network. Finally, let's attach our router to that external network and set it as the gateway. What happens now? Our router got an IP assigned from the public network. Moreover, SNAT was automatically enabled. That means all our VMs will be able to reach the internet as their source IP will be translated to the IP of the router. Here's how it looks on the diagram. Let's test that. I will connect to VM1's console and try pinging Google DNS. Works. So, your VMs are running safely inside their isolated private network. But what happens when you need to expose one of them, like a web server, to the outside world? How do you give it an external IP without compromising the security of the entire private network? This is where floating IPs come in. A floating IP is an external IP address that you can reserve and then dynamically associate with any of your VMs. It acts as a static, public-facing address for your instance, while the instance itself keeps its private IP for internal communication. First, we need to allocate a floating IP from our external network pool. We are asking OpenStack for an external IP that we can use. Now that we have our new floating IP, we can attach it to VM1. The command is simple. OpenStack server add floating IP followed by the name of our VM and the floating IP we just created. So what's happening behind the scenes? The OpenStack virtual router is setting up a one-to-one NAT. Any connection from the internet or the external network to the floating IP is automatically translated and forwarded to the VM's private internal IP. When the VM sends traffic out to the internet, the router translates its private source IP into the public floating IP. The beauty of this is the name floating. The IP isn't permanently tied to the VM. You can easily detach it from the instance and reattach it to another. This is incredibly powerful for maintenance, upgrades, or high availability scenarios without ever needing to change public DNS records. That's a wrap on our beginner's guide to OpenStack Network. You now have a solid understanding of the essentials, from creating isolated tenant networks with vxlan to providing internet access with floating IPs. However, this is just the beginning. The world of cloud networking is vast, and there are many advanced topics to explore next. How do you attach to multiple physical networks or VLANs? What are the best practices for designing a complex network topology? How do security groups function as a stateful distributed firewall for your VMs? How can different projects talk to each other securely? What's the best way to add a virtual firewall appliance? What are the pros and cons of OVS versus OVN? How do you set up a high availability and distributed virtual routing? If you want to master these topics, smash that like button, subscribe for more OpenStack content, and hit the notification bell so you don't miss my next video. Thanks for watching, and I'll see you in the cloud.